Hi, my name is Shahnawaz. In this lecture, we'll finally prove the fundamental group of a circle is actually isomorphic to the group of integers. So we have this theorem here. So let us pick B any point in the circle, say S1. So let B be a point of the circle S1. Then the fundamental group of S1 based at point B is isomorphic to the group of to the additive group of integers, that is phi1 of s1b is isomorphic to z. Now let us prove this. So without loss of generality, we may assume that the point B is actually the point 1 0. So without the loss of generality, we may assume uh, that this point B is the point 1 0 on the circle. So we have this S1 to be the unit circle. So this, let us draw this S1. Suppose this is a point B, which is a point 1 0. So actually this is the y-axis, this is the x-axis, this is the point 1 0. And let us embed R into R3 as a helix. So this is R here. So if this B is a point 1 0, then the map P from the real line R to the unit circle S1 defined by P of S is actually cos of 2 pi S sine of 2 pi S. So this map is actually a covering map. So this is a covering map. Now one can note that if we uh, look at the point P of 0, that will be cos of 0 sine of 0, and that is the point B. I mean that is a point 1 0, which is a point B. So note that P of 0 is the point 1 0, which is point B. And if I look at the inverse image of point B, I get the set of integers, because if we put any integer here, suppose p of n, then we get cos of 2n pi sine of 2n pi. Now cos is equal to 1 at the even multiples of pi, and sine is always equal to 0 at any multiple of pi. So that means any integer is mapped to the point B. So hence the inverse image of this point B will be the set of integers. Now let us do one thing. Let us draw this a little bigger. So it is like this. So this point has these points as pre-images. So these will be the integers on R. So this is the real line R, and these points are the integers. So this P has these points as pre-images. Now let us choose some loop on S1. So let gamma from the interval 0, 1 to S1 be a loop based at, let us be a loop based at B. Now this gamma is a loop on the circle B, so this gamma may look like this. So first, so it will travel alongside the circle, or sometimes it may change the direction, or sometimes it will first go in this direction, then it may come back. So the point is that this gamma is based at point B. So then the homotopy class of gamma is going to be an element of the fundamental group of S1 based at point B. Now by path lifting property, this gamma has a unique lift which will start at 0. So by path lifting property, there exists a unique lift, say mm, say gamma tilde, which will be a loop, which will be a path from 0, 1 to the real line. So let us pick this loop here. So this loop may have a lift here. Let us denote that lift by this thing over here. So this lift of gamma starting at starting at 0. That is, if we compose P with gamma tilde, we get the map gamma, and this gamma tilde starts at 0. Here we have the map P from R to S1. We have the map P. Now note that gamma tilde of 1, so gamma tilde will be equal to the P inverse of gamma. So gamma tilde 1 will be equal to P inverse of gamma of 1. But we know that, so this is equal to P inverse of B. I mean, this is the belongs here. Gamma tilde will be an element in this uh, set, and this set is actually P inverse B, because uh, gamma 1 is actually B here. So that means gamma tilde of 1 will be an integer. So hence gamma tilde of 1 is an integer because this P inverse B is equal to Z. Let's write this down here. So P inverse B is Z, hence hence gamma tilde of 1 is an integer. Now that means if we take any loop in S1, the left of that loop will end at some integer. And because one can see here, we chose this gamma to be a left on S1. Then it is left, which is gamma tilde. It ends at an integer because gamma tilde of 1 is an integer. Now we claim that there is a well-defined function. So we claim that there is a well-defined function, say phi, not a function. We claim there is a well-defined homomorphism. Phi from the fundamental group of the circle based at point B to the group of integers which maps the homotopy class, which maps the element, say homotopy class of gamma in this group to the endpoint to the endpoint gamma tilde 1. So where gamma tilde is the left of this gamma of the left gamma tilde of gamma. So first we'll show that this phi is a well-defined map, and for that uh, we know that since P is a continuous map from R to S1, so this P will induce a homomorphism. So since P from R to S1 is a continuous map, mm, we have the homomorphism P star from the fundamental group of this real line based at say 0 to the fundamental group of S1 based at point B. This we had done in the I think in previous lecture, that any continuous map induces a homomorphism between the fundamental groups. So this homomorphism is induced by P. Now one can note here this R is simply connected, so it is fundamental group will be trivial. So since R is simply connected, uh, the fundamental group of R is actually the trivial group. I mean, it will contain the homotopy class of the identity element of this group, where ER, where this ER is the identity of phi 1 R 0. So therefore, if we look at the P star image of this group, then we are looking at the image of its identity element, which is the P star image of the identity element. And since P star preserves the identity element, it will map this identity element to the identity element of phi 1 S1B, that is noted by ES1, where this ES1 is the identity element of phi 1 S1B. Now we have to prove this phi is well defined here. So for that, let us take two homotopy classes to be equal. So now let the homotopy class of F is same as homotopy class of G, where F and G are the loops in S1 based at B. Based at the point B. So if they are the loops in S1, so they must have their unique lifts. So let F tilde and G tilde be their unique lifts starting at 0. That is, this composition map is F, and the composition map P composite G tilde is G, and F tilde starts at 0, so does G tilde. Now we are given that these two homotopy classes are equal. So therefore, if I look at this class of F product with the class of G inverse, what we get? We get the identity element of, I mean, we get the homotopy class of the identity element of ES pi 1 S1 of B, which is ES1. Now this ES1 actually belongs to the image of P star. So one can note that this homotopy class over here is actually equal to the homotopy class of F product with G inverse, which will be this element and which is equal to the P star of uh, pi 1 of R0. Uh, since we did 11 in last lecture, where we proved that this homotopy class is in the image of P star, if and only if uh, their leptos agree at their endpoints. I mean, if f tilde of 1 is same as g tilde of 1. So this is true. This is true if and only if f tilde of 1 is g tilde of 1. This follows by previous lemma, which we did in the last lecture. Now, if f tilde of 1 is g tilde of 1, this will imply phi of homotopy class of f is same as phi of homotopy class of g, because that is how we defined this phi over here. So this phi is defined like this because phi takes the homotopy class of gamma and it maps to the gamma tilde of 1. So therefore phi of uh, phi of homotopy class of f will be equal to phi of homotopy class of g. So we started at this thing. I mean, we took these two elements to be equal and we proved their phi image is equal as well. This proves the well-definedness of phi. So hence phi is well defined. Now let us prove phi is injective also. The map phi is also injective for if phi of homotopy class of f is same as phi of homotopy class of g, where the homotopy class of f and homotopy class of g are the elements of the fundamental group of S10, then uh, f tilde of 1 is equal to g tilde of 1, or mm, this homotopy class belongs to the p star of p star of pi 1 sorry pi 1 of r0, which is actually the trivial subgroup es1. So this shows that the homotopy class of f dot g inverse is the homotopy class of es1, or homotopy class of f is same as homotopy class of g. So this proves the injectivity of the map phi. This map is also surjective. Now to prove phi is surjective, Mm, we have the loop. So we have a loop uh, gamma. Let us call this gamma n from from 0 1 to s1. So this is a loop in s1 based at point b, and this loop is defined by, so this loop is defined like this. So gamma n of s, so this is actually equal to p of ns, and p of ns will be the map cos of 2 n pi s sine of 2 n pi s. So this gamma was actually the loop cos of 2 pi s sine of 2 pi s. So it is like this. So gamma 1 is actually gamma. So gamma 1, so this is our circle here. So this is the point B, which is the point 1 0. So if we vary s from point 0 to point 1, we get a loop which turns around the circle one time. So for n is equal to 2, we have cos of uh, 4 pi s sine of 4 pi s. So that means as we vary s between the interval 0 1, this loop will travel around the circle two times. So for n is equal to 2, we have a loop which turns this circle two times. So for uh, general s, this loop will turn around the circle n times. So now we have to look at the lift of this gamma n. So that means since we have the real line here like this, so let us mark this as point 0, this is point 1, this is point 2. So if we look at, I mean, if we take n to be equal to 1, then we have a loop which travels this circle one times. Then we have the lift which starts from 0 and ends at 1. For n is equal to 2, we will have the lift, we have a loop on the circle which travels the circle two times. Then we have the lift here which starts at 0 and ends at 2, and so on. That means for uh, any n, uh, the loop on the circle which travels the circle n times, the lift will start at 0 and end at 1. So therefore therefore for every integer n in z, uh, there exists the homotopy class gamma n in the fundamental group of the circle based at B, such that phi of gamma n will be gamma n tilde 1. Now this gamma n tilde 1, this end is at n. The reason is that because since gamma n tilde is actually the lift of gamma n, so that means p of gamma n tilde will be gamma n, or gamma n tilde of 1 will be p inverse of gamma n of 1, but gamma n of 1 is p of n, so this will be p inverse p of n, and this will be sort of integers which contain n as well. So since this gamma n tilde is unique, this has to be equal to n. So this proves the surjectivity of phi. So hence phi is surjective. So what we prove here, we have phi, the map from pi 1 of s1b to z. So we chose any integer n here, and we proved that there is some gamma n in pi 1 s1b whose image is n. Now for negative integers, this index here, this will be minus n, because in that case we had the loops in the other direction on the circle. Now finally it remains to prove this phi is a homomorphism. So finally we claim phi is a homomorphism. Now for that, let us pick two loops. So let alpha and beta be two loops in S1 based at uh, point B, and let alpha tilde and beta tilde be their unique letters starting at 0. That is, B composed with alpha tilde is alpha, P composed with beta tilde is beta, and alpha tilde of 0 starts at 0, and so does the beta tilde. Now let us define another loop gamma to be the product of these two loops. So let gamma from 0 1 to s1 be the product of loops alpha and beta. The loops alpha and beta, that is, this gamma is the product alpha beta, and hence this gamma will, I mean this gamma of s will first travel alpha of alpha at twice the speed in the interval 0 to half, and then it will travel beta in the next half interval at twice the speed. So we have this gamma a loop in S1. This is based at point B as well. So then by path lifting property, this gamma again has a lift. So let gamma tilde from interval 0 1 to R be the unique lift of gamma. starting at 0. That is P of gamma tilde is gamma, and gamma tilde of 0 is 0. Hence, this gamma tilde of S will be in the loop like this. So in the first half interval, it will travel alpha tilde of 2s. So if s is between 0 and half, and in the next half interval, it will travel alpha tilde of 1 plus beta tilde of 2s minus 1. So if half is less or equal to s is less or equal to 1. Now, why we uh, take alpha tilde of 1 here? So we take alpha tilde of 1 to make alpha tilde continuous, because since alpha tilde is continuous, beta tilde is continuous, so this is continuous. So now it has we need to check only continuity at half. Now alpha tilde of half will be uh, alpha tilde of 1, and here alpha tilde of half will be I mean the left hand limit is alpha tilde 1, and the right hand limit is alpha tilde of half will be alpha tilde of 1 plus beta tilde of 0. Beta tilde of 0 is 0, so that is 0. That means if we do not take alpha tilde 1 here, this alpha tilde will not be continuous at half. So that is why we choose alpha tilde 1 here. So thus phi of this phi of the homotopy class of alpha product with homotopy class of beta. So this will be equal to the phi of the homotopy class of alpha product with beta. So this is the product now composition. So this will be uh, phi of homotopy class of gamma. Now gamma phi maps this homotopy class gamma to the endpoint of its slipped. I mean, it will map gamma phi of gamma tilde to phi of homotopy class of gamma to gamma tilde 1, and gamma tilde 1 here will be alpha tilde of 1 plus beta tilde of 1. This is alpha tilde of 1 plus beta tilde of 1, and alpha tilde of 1 is actually phi of the phi of the class of alpha plus phi of the class of beta. So this proves this phi is well defined also. Sorry, and this proves phi is homomorphism. So therefore phi is a homomorphism. Hence, the fundamental group of the circle at 0 is isomorphic to the group of integers. So this is one of the important results in algebraic topology. Now in the upcoming lectures, we'll prove this. We will prove some applications of this result, which includes the fundamental theorem of algebra, Brouwer's fixed point theorem, and some other applications as well.